Hi everyone, I'm Pranoti, host of Under the Microscope. This series is brought to you by the Real Scientists Nano team. Our goal is to provide a platform where scientists can communicate their work and interact with the public. With that in mind, every week we introduce you to a scientist working in the field of materials or nanoscience, who tweets from the Real Scientists Nano Twitter account, which is realsci_nano.
Hi everyone, my name is Pranoti. I am your host of the Under the Microscope series, podcast series, and today we have a very special guest with us. Please welcome Sara Hernandez Mejias. I hope I pronounced that correctly. Sara is a senior researcher at the Madrid Institute of Advanced Studies in Nanosciences. Of course, in Madrid, in Spain, in Europe, which is on Earth. And Sara also recently joined the Real Scientist Nano team, the Science Talk and the Real Scientist Nano team. So welcome, Sara. How are you?
Thank you. I'm fine. Happy to be here, a guest in this podcast. It's also very special for me. So thank you for inviting me.
Of course, we are very happy to have you here. So let's dig in. Could you explain your research to us in super simple words, please?
So I do mainly research in light conversion and trying to use light as an energy source. So basically what I'm doing is design photosystems that I can tune on demand and try to optimize them just to harness the power of the light as an energy source for different applications, including photochemistry, nanophotonics, depends on the system that I build.
Wow. Oh, wow. That sounds so cool. Okay, I have so many questions. So how did you get to be the senior researcher, like now the research that you're doing? Could you tell us a bit about your research journey, like the career journey so far?
So I am physicist and I'm very proud of being physicist, but also I'm very interdisciplinary. So when I finished my bachelor, I just needed to choose a path and I decided to do a PhD. And I heard about new materials and biomaterials, so I just decided to go there. And it ended up being very much molecular biology. So very far from anything that I studied in my bachelor. So it was a big shift. So I did all my PhD in protein design, and I was building nanosystems with cool tune and the nanoscale, and depends on the nanostructure, they change the macroscopic properties. So after my PhD, I enjoy a lot learning this molecular biology part, but I really felt that I wanted to know more into mechanistic studies and this kind. So not only build the material, but also study the mechanism. So I decided to proceed with a postdoc, but now more focused in time-resolved spectroscopy, which is a technique that allows you to know a bit the light conversion mechanism in systems. So I did a postdoc of 6 years now, so quite a long postdoc already, in laser spectroscopy and time-resolved spectroscopy with different systems. And now recently, I'm super happy because I get this grant at a grant as a junior leadership. So I will start my own group in October, combining these both worlds, more the molecular biology and spectroscopy in one team. So we are going to be working in this light conversion mechanisms in engineered photosystem based on proteins. So it's very nice. And
yes, go on.
Yeah, related with this journey, is very interesting to me something, because when I finished my bachelor, I was considering to be a nuclear physics, so I really was into nuclear physics. But then I said, this sounds very cool, but also it sounds like you are going to be abroad in different countries and everything, and I was not feeling ready for that. And I was a bit naive because then I've been in Sweden, I've been in the Netherlands, and really I'm very happy that I had this super international journey, that I met many people of different countries and I really learned. But it's something also curious from the journey. How you make decisions depends on what you feel that is going to be about, but then it's completely different.
Yeah, absolutely. That's really interesting that you considered being a nuclear physicist, but then you decided against it, but then ended up being a traveling scientist. It's just that's amazing. So, about your current research with the spectroscopy and the molecular biology, like with the molecules, are there any specific molecules that you are working with, or is it like the whole range? Like at the end, I would like to know what is your favorite molecule if you're working with a few. That's where I'm headed here.
So I'm working mainly with organic dyes. So these dyes are made by aromatic rings. So depends on how many aromatic rings they have. These electrons are like moving around all the molecule. So depends on the structure. You can have different absorption properties. So I don't have any favorite molecule because I use depending on. So depends on what system I'm using and depends on the application that I want to go. I use in different molecules. For example, I use BODP. This is kind of molecules that I'm using. That is very interesting because you can tune the structure to have different properties. But also one of my favorite now is pyrene molecule. This is done by 4 benzene groups. That is the one that I'm working with now. This is very interesting one because when you excite your molecule to the excited state, then have different decay pathways. So now we are just making proteins in order to tune this pathway selectively. So I will say BODP and pyrene, perhaps for now, but let's see in the future.
So you do have favorites. Okay. Okay. So if I understand this correctly, if I understand you correctly, so there are these molecules or like a bunch of molecules, and then you shine laser on them, and whatever comes out or comes back or comes out is what you've studied. That's the spectroscopy part. Is that a fair way of saying it? And then, of course, it's more complicated. But if we have to oversimplify, there's a molecule, you shine laser on it, and then see what happens.
Yeah, that's it. So what you would do basically with the laser is you excite your molecule. So this molecule takes the energy of the laser. So it goes to the excited state and is from there. So the light conversion is basically converting this light that is reaching the molecule to another state. It can be electrons or it can be a photon with another energy. So what you observe is how from when you excite your molecules is how it evolves during time until the nth step. So you are able to see these processes, and you can be. So I work with different lasers. One of them is in the femtosecond range. So it's really taking 1 second and dividing 1 billion times. So it's like quite fast processes. And then I have another one. So I have another laser in the nanosecond range. So it's just 10 power to minus 9 seconds time. So you work in this range time.
So so with the femto laser, which is 10 to the power minus 15 seconds, so 1 divided by a billion, 1 billionth of a second, with that you would be able to understand that's where the time resolved part comes in, like what happens on a femtosecond level in the molecule. And with the nano laser, it's like what happens on a nanosecond level. What processes happen? How does the molecule react, or what happens to the molecule? So that kind of information, right?
Yeah. So the thing is that you have some processes that are very fast. So for example, all the thermal relaxation in the molecule, also things that happens intramolecularly and interacts very quickly with the proteins. This happen in the femtosecond time scale. So they are very quick processes, but there are other processes that, for example, rely on interaction, like diffusional processes, for example, these kind of things that are slower because you are not already in the molecule, but you are interacting with different molecules. These kind of things requires time. So it's fast still comparing with our life because it's nanosecond, but it's a slower processes. So you can define all these two processes, like things that happen in the two ranges of time.
That is so cool. Oh my God, that is so cool. Wow. Oh my God, that is so cool. Okay, so now I want to ask you this because you work with molecules, you work with lasers, you work with these super fancy lasers. But before I ask that, which lasers are we talking about here? Are we talking about green, red, blue, or is there like a range of lasers?
So our laser generates a light in the infrared, so 1075 or something like that. But then you can tune this one. So you have your fundamental, but then usually when you have a light, you have also different harmonic that you can just tune with some crystals. So there are some crystals that are are called non-linear crystals. So you can choose the fundamental, the first harmonic, the second harmonic. So you can go from this one in the fundamental, then choose also, for example, around 532. So this is more in the visible part. And then go for the UV, for example, 355 nanosecond. So this is basically the light that you can achieve from the laser. But then we have also a very different systems that are composed by different combination of crystals that allow us to convert this light in any light that you want in the visible range, UV range, and infrared. So any light that you need, any light that you need to pump your molecule, you can achieve with this kind of system. They are called OPOs, no-pass, this kind of. So there are combination of crystals that just basically depends on how they interact with the light. They convert a wavelength to another wavelength, and you can tune them to achieve the wavelength that you have. Because of course, so there are some molecules absorbing in the UV, there are other molecules absorbing in the visible, there are other processes that you want to know that absorbs, for example, in the infrared. So you want to have a range of light to prove it.
Yeah. Okay, wow. That sounds so cool. Because during my PhD, I think I worked with a red laser and I think I worked with blue and green. So 488 and 532. I think 532 is green, not blue. Yeah. I get confused now. Wow. I should remember these things.
It's very interesting because you can really. So I also, when I was learning about lasers and this kind of tuning, I feel that is really, really interesting. And the problem is that sometimes they are not very efficient because you have a lot of loss in each crystal. So if you put many combination of crystals, if you really need to tune your light, you need to put a lot of combination. You lost a lot of power. Sometimes you need higher power. So there is a lot of research on these kind of materials that tune the laser lights and these kind of things. For example, in my group, there are some people working in lasing. So they do, for example, different cavities that can have these different laser properties. So like this, you can have more tunable lasers, and it's very relevant for example, for me, that I want to understand other kind of systems.
Right. That makes complete sense. Wow. So it sounds to me, Sara, that you have been involved in a lot of interesting research projects or experiments. If you have to pick one research project that you're most proud of, could you pick one and explain it to us in simple words in the section we call In Other Words?
So I will choose the one that I'm working now. Indeed, now I'm not in Spain, I'm in Sweden now, just finishing that project. So it will be published soon, I hope. So in this project, what I like in this project is that it's the first time that I really mix the molecular biology with spectroscopy. So basically what we have is this pyrin molecule that I was talking about. And so we embedded this pyrin molecule in a simple protein. This protein we can tune, like at the nanoscale, because we know exactly the structure and what amino acids we can tune. So what we observe is that just tuning a single amino acid in the protein, we can induce some quadrupolar interactions. So these are electrostatic interactions in order to tune the structure of the protein. So just one amino acid tunes completely the structure of the protein, and then we can do a selective light conversion. So going, for example, to have more charged state. So this pairing, when it gets excited, it decays with 3 different pathways. One is forming electrons, like charged states. Another is forming one spin state different from the excited state, so it's the triplet state. And another is just emitting fluorescence. So what we observe, so in the planar molecule, this conversion is not selective. So it can go, it has a quantum yield for each of them. So you are losing energy. Imagine that you want electrons. At the end, you are losing energy there because you have also the other path. So with the protein and tuning the structure, we can select one path or another. So favoring, for example, charge formation, forming a fluorescent, or forming the triplet state. And it's very cool, I think.
It is, yeah. It sounds really, really cool. So this was a project that is in Sweden, you mentioned?
Mm-hmm.
Okay.
So yeah, I started here. I've been here 2 years as a postdoc, and I started here this project. It was I started here the project, and now we are finishing. And I will follow my career path through that path of modifying proteins to do selective light conversion. So the idea started here.
That is so cool. So you must be really, really proud of this.
Mm-hmm. I really like it.
I hope it will be published soon so that we can all read it. Would you be able to talk about it a bit when you're taking over the Twitter account?
Repeat again, please.
Would you be able to talk about this project when you're taking over the Twitter account as well? I know the research is not published, but
I think that is fine.
That is fine. Okay, that's cool. That's really cool. So, Sara, I mean, research is one big part of being a scientist. But what else do you like about being a scientist other than the research itself?
So, one thing that I like is that you can really do research in things that you like it, right? But I like to do it with a team. So one thing that I like is that you can choose what person you want to involve in your team and work together in that project that you like it. So this is one thing that I like it. Mm-hmm. Also, so I really like to do this networking and all this international environment that we are exposed on when you are a scientist, that perhaps if you are working in a small company in Spain, you have not. And I think that it really enriches you as a person to be in this international environment.
Right.
And I think that this is my main favorite thing. So building a team and this international environment that you are involved in.
That's really cool. And I hope you will soon be able to start, you will be able to start building your team. I'm super excited for you about it, about that part of your career and that part of your personality as well. Sara, I hope your research experience has been wonderful and will continue to be wonderful in the future as well. I mean, it sounds to me that it's worked out very well for you, and also congratulations.
It was challenging, but
of course, yes. So regarding the challenges, if you had 3 wishes to improve your research experience, what would you ask for? And I'm not promising anything here. Sorry.
So I think that one thing that I would like is to invest more time with people that inspire me. So sometimes the researchers don't have time, like senior researchers don't have time to talk with you and these things, but I would like to have more time to sit with them and just discuss about research, but also about life, I mean also what path they choose. So have this kind of conversation with people that I consider that are inspiring. So this was the first thing. The second thing that I will ask will be, so now I start to do networking, but I would like to have the chance to network more. because I really enjoy this collaboration. I think that they are really important part of the research also, like having a collaboration that you can put all the expertise together. So I would like to have a bigger network working on that still. And then the third thing, I think that I would love to have a stable funding. So forever. So this will be my 3 wishes.
Okay. So to be able to speak with people that inspire you, stable funding, I think that's just, yeah, that's very, very, very important. And more opportunities to network. That sounds amazing. And I'm sorry?
Sorry. No, say.
Yeah, no, I was just saying, these are quite realistic wishes, to be honest, and I hope they will come true soon enough. So Sara, this has been wonderful talking to you, learning about your research, learning about you as a person, as a scientist. So what can the followers expect in the week that you will be taking over the Real Scientist Nano Twitter account?
Can you repeat again the question?
What can the followers expect in the week that you are taking over the Twitter account, the Real Scientist Nano Twitter account?
So you mean what they are going to have here?
Yes. What are you going to tell us about when you are tweeting from the account?
So I think that this one
about your research, about your career, about your papers, about
okay. So yes, in my Twitter account, they will know about my research, about my career a bit. Also, I tweet a lot some advices for young people, and also some wishes. I used to tweet about some wishes also. I think that this one.
Okay, that sounds cool. And I hope that we will get some nice pictures from your lab and from your institute and from Madrid as well. It has been my wish since a long time to visit Madrid and lots of other parts of Spain as well. So I look forward to having you on Real Scientist Nano. Thank you very much, Sara, for speaking with me.
Thank you for hosting me.
Thank you for listening. This is Pranoti, host of Under the Microscope. To know more about us, visit our website, thesciencetalk.com, and follow us on Twitter at realsci_nano.